Welcome back to General Ecology. We're in the basically in the section from chapter 4 on predation and herbivory, predation with prey, herbivory, plants, I suppose you can call them prey, seeds, things like that. But you could, everything I'm talking about, you could kind of move back and forth between organisms like animals and organisms like plants, or even bacteria and all that. These models will work. Today's section is on developing further the exponential growth models that we learned about a couple sessions ago that were very simplified. Boom, you grow and you continue to grow. Okay, no, there are checks on growth, and so there's the logistic growth equation, and you have crowding and things like that so that it levels off to carrying capacity. So you're going to see these models today, but we're going to do something else. We're going to add another species. That is, we're going to have interactions between predators and their growth and prey and their growth and how they interact with each other. Still fairly simplistic math, and so we could model it without tremendous computer power, even back before there were computers developed. So I think it's instructive to walk you through these models. If you go on in ecology and become a population ecologist, if you take a course in population ecology here at ESF or elsewhere, you will see these models again and use them. What I want you to get today is like in the other setting with just the logistic growth models and such, know what they're showing you. Know what the different factors are telling you and understand the theory behind it, but applying it we will not be doing. But you'll be able to interpret figures and see things, and you say, oh, okay, I know what they're talking about. They're talking about a predator-prey model, Lotka volterra, and that should ring a bell. Okay, so that's what we're going to talk about today. And I'll open up with, again, this is all chapter 14. And you can see here, this is the classic lynx and hare, snowshoe hare, and talked a little bit about it, but you can see the lynx peaks are offset from the snowshoe hare. And basically that's because the hare has to grow in its population in order for there to be enough resource, i.e. food, prey, for the lynx to now start capitalizing on that in a sense and start eating it up. And then the lynx becomes very abundant, the numbers. But now, because they're there, they're eating the hare, which then start to drop off, which then starves the lynx, which then releases the hare, which then, okay. So we're going to look at how that can be modeled in today's presentation. So we are continuing to expand, as I suggested, the exponential growth model. And so if you recall, the exponential growth model is dNTT equals Rn. And that's the population growth under unlimited conditions, unlimited growth. So that D represents change. Just to review here, the change in the population size over the change in time equals the intrinsic rate R of growth for that population times the current population number. Okay, that's the model. But as I said, we know that it's not just unlimited growth. There are things that control growth. And the primary one that we've talked about, or the primary concept that comes into play usually, is density-dependent factors, crowding. There aren't enough resources to go around. There's too many bumping shoulders and sharing germs, so disease becomes a problem under crowded conditions, etc. Okay, so then we model, we add another component that's basically carrying capacity. So we're still looking at the growth over time times the intrinsic rate of growth times the population, but we add this factor, is basically the intrinsic growth, the carrying capacity factor, K. And so That's the logistic growth model. As you approach carrying capacity, this basically slows your growth down in the mathematical model, and you can show that the real populations are following very simplistic mathematical model parameters there, and the model works quite well. Okay, but we're still only dealing with a single species, right? And so now it starts to get interesting because we don't work out in the real world as a single species. We'd like to think so, some more than others. But now we're going to add that second species and start to build on that model. And two guys, they were guys, kind of came up with this model independently, if I understand correctly, Lotka Volterra. And they modified that exponential growth model. And so this first one, we now have to have two different equations, one for the prey and one for the predator, okay, or the herb and the herbivore, all right, the resource and the consumer. All right, so we're going to have two different ones. This first one's for the prey, the resource, and you can see it's fairly simple still. dNTT equals Rn, that part is familiar, but now we subtract the predator's consumption of the prey. So C, the consumption, N, population of the prey, and then P is the predator. So how many predators are there? How many prey are they eating? Okay, so in words, the prey population growth over time equals the growth of the prey minus the consumption of prey by the predator. Consumption of the prey and by the predator P. And here are what those different variables represent. And I add in here, I didn't add the R because you remember that, right? We don't need to review that again and again and again, even though I just did. So if you don't know R by now, make sure you do soon. Okay, so we could do the same thing, only it's modified now for the predator instead of the prey. All right, and it's a slightly different equation. Still modifying the exponential growth model. And now we have the change in the predator population. Instead of N, we're switching in P for predator over the change of time equals, okay, this is getting crazy, ACNP minus MP. Okay, N is prey population, P is the predator population, but what's this stuff? You recall that it used to be Rn. So this is basically a function, this is basically modifying the intrinsic rate of growth for the predator to incorporate its consumption of the prey and its assimilation of prey and turning it into offspring. So instead of R, we say AC for consumption and assimilation or conversion into prey. Into predators. M, and I'm going to define all this further in this slide, but M is just the mortality. It's the rate of mortality, much like the Rn used to be the rate of intrinsic growth. MP is the rate of intrinsic death for the predator. So you're subtracting predators at this end, you're adding predators at this end for the predator model. All right. So in words, population growth of the predator over time equals the growth rate of the predator minus the death rate of the predator. And ACN, as I was just describing, this here is just a modification of R, the intrinsic birth rate, but now for the predator, and it incorporates the consumption and assimilation or conversion of those prey into predator. And then again, M is intrinsic mortality rate. I've already described that. Okay. So in summary then, putting those two concepts together, that is the predator and the prey models, they are modified exponential growth models. Here they are for the different factors, the prey and the predator. And then here, this is what all those variables are referring to. N is the prey. So sometimes we say victim. It became hard because you had to leave. You would like to use P for prey, but you can't because it's kind of been decided that that refers to P predator. So some people say V victim. You might see models with V instead of N. I just left it as N here. Just know that's the prey, and the P is the predator. Okay, and then here, as I've said a couple of times here, efficiency of capturing the prey is C. A is the predator's conversion of prey into predator offspring, if you will, and then M is mortality. These are just derivations of that exponential growth model, if I haven't already made that clear. Okay. So to look at the prey population, we start with that equation, and then we could say, okay, with no growth, dNTT equals 0. There's no change over time. Okay, if that's the case, then Rn, C, and P, the other half of that equation, equals 0. There's no growth. And then you can play around with this to kind of tease apart what those different variables are doing. So we rearrange this equation on this side, subtract Rn from both sides, and rearrange. In other words, get rid of that negative sign on both sides. If you subtract, well, you could subtract C and P, and then it becomes Rn equals C and P. Okay? So when there's no growth, the rate of growth of the prey should equal the rate of growth of the predator, or the consumption of the prey is equal to the rate of growth of the prey. Okay, consumption by the predator. All right, if we divide both sides by n and rearrange, we come up with this. So if you divide both sides by n, it's R equals CNP or CP, and then you could divide C and it becomes P equals R divided by C. P equals R divided by C. Now I go through that fast and sometimes skip along a little bit, but you can do that without a whole lot of effort. It is just basic logic, algebra. Now the prey will increase here, so intrinsic rate of growth of the prey will be greater and allow it to increase greater than the consumption by the prey, or the prey will decrease if that intrinsic rate of growth is actually less than the consumption by the prey. The predator eat more prey than are being eaten by, being produced by the prey. Okay, so different conditions yielding increases or decreases in the prey population. Or actually the predator population. Well, we could look at that. Let's see. So same kind of thing, you can look at the equation, you set it to 0 growth, all right, and we can take the equation over here and say at 0 growth, ACNP minus MP, you could subtract both sides by MP, and now you have ACNP equals MP, as in here. And when there's no growth in the predator population, okay, that's what this is asking, then the predator growth is equal to the death of those predators, MP. So you have that equal sign. Divide both sides by ACP, then we come up with this, N equals M, cancel out the P, M divided by AC, because we divided both sides by ACP, N equals M divided by AC. And back to these kinds of manipulations, the predators will increase when the population of prey is greater than the predator mortality and ability to convert those prey into more predators. So that's when you'll get an increase in the predators, is when you have more prey than the mortality, and therefore the predators go up. Predators will decrease when you have less prey production than the mortality, and therefore the mortality overrides the production of the prey, and there's not enough prey to feed AC, to feed the predator population, and so the predators will decrease. All right, this is all, I'm sure if you're not following directly, go back and review it, look in the book. It's all very logical. It's just a lot of information that comes flying at you at once. But it all makes sense if you just carefully go through and look at it and understand what the different factors mean. And that's, again, And that's what I want you to be able to do. What does M mean? What does AC mean? What happens if AC goes up? That is conversion of prey into predator. Well, the predator population goes up. What happens if mortality goes up? Well, predator population goes down. Okay, there's more mortality. If there's more mortality of the predator, what happens to the prey? Clearly, it goes up because it's not getting eaten as much. Too many predators have died. Okay, you can mess around with that. Now, there are some really interesting graphics of these concepts. And I like this summary graphic. The book kind of develops it a little bit further. These lines, the X lines, are the isoclines. So this is the isocline of the predator, because we're looking at the number of predator in the population. And at this point, that's the 0 point, where there's no growth or loss of predators in the population. And then a similar one over here with the number of prey, where you have no gain or loss of the prey because they're getting eaten, basically, by the predator. All right, but you can put everything together. You can have them all separated, or you can put them all together in this joint equilibrium graphic. And we could walk through here. I think it's kind of instructive. So the number of prey on the x-axis, number of predators on the y-axis. We'll start over here. There are so few predators that the prey will increase. They're not getting eaten. And so, but the predators don't have enough prey to eat yet, so the predators are still going down. If you follow this curved arrow here, or vector, predators are going down, but now the prey are starting to increase because there's not enough predators to eat them all up. And so you're moving right, increasing prey populations, but you're moving down because the predators are still dying off in this sector. Cross over that isocline line, and now there are enough prey to feed the predators, and both prey is still increasing, but so are the predators, and so the arrow, the vector curves up. Cross over the line, now there's too many predators, so they're still going up. There's enough prey to continue to feed that population, but now they're starting to eat more prey, and as a result, the prey population is dropping and moving to the left, right down here on the x-axis. And same thing here. Now you don't have enough prey to feed all the predators, so not only are the prey going down, prey population, so is the predator. And eventually you cross over where there are fewer predators, but that's releasing the prey to start increasing. And it keeps just going round and round, and it's never as smooth as these beautiful mathematical models suggest, but populations behave this way, predator-prey. All things being equal. In other words, everything else being out of the system, just the two species, which is an interesting assumption that we'll address in a minute. Okay. Now, I should say, and I neglected to say this earlier, but all of these sort of mathematical models and concepts and things in the lectures that you're watching are going to be fodder for the flipped classroom idea, both with me in a chat room, but also with your TAs, so that as you have questions, write them down and prepare yourself for going into those chat rooms and saying, what the heck was he talking about AC? I have no idea what AC means. It's like, isn't that a type of electricity? AC, or is it a band, AC/DC? Anyway, hear what I'm saying, start to get some questions, and those questions will help you synthesize and understand these concepts better. So you are utilizing these, the flipped classroom approach like that. All right, so as I said, this is a mathematical model of predator-prey interactions. And this, if you remember, this all started with the image where I think it was the lynx and the snowshoe hare. The snowshoe hare population goes up. The predators start to eat them. They go up. They eventually cross a line. The prey starts to drop off. The predator continues to grow, and then it crosses a line. There's not enough prey anymore. Now the predator population drops off. Okay, so This is what this is modeling. If you look over here on the right side, the colors that you see in the left side are represented in the colors over here. And you can say, okay, in this blue area where there's not enough prey to feed the predators, but the predators are still eating the prey, so both populations are going down, that's this blue sector right here. Both populations are going down, right? And then you get into over this section, and the prey begin to increase, but the predators, the red line here, are still going down, but the prey is rebounding. All right, so you could see any sector in these classic kind of wavy figures are represented in this beautiful model that Lotko-Volterra gave us. The joint population trajectory, and then there's this joint equilibrium point. There's no way they stay put. That may be a theoretical location where nothing changes, but one perturbation, like a bad storm, and the prey population gets knocked down just a little bit, and that's going to knock everything off the equilibrium point, and now you're back into the cycling with prey and predator interacting with each other. But it's we love our equilibrium points because it theoretically makes a ton of sense, but ecologically, I dare say it doesn't make much sense at all. Just a mathematical point. So here are, again, here's the snowshoe hare and the lynx on the right, the Huffaker's mites, where he was able to generate the cycling for, 200 plus days. You could see, and in fact, you could draw these locations and bring them over to this figure to actually catch that the model works in the real world, or laboratory world as it were, or in the real world over here, right? So, but these are simple. I want to emphasize that. They are simple. Here's one more. I kind of pulled this out of your text from figure 15. Again, it's the snowshoe hare lynx model, and it's actually real data where they're showing you the number of hare on the x-axis per hectare, per 100 hectare, and the number of lynx. And you can see that the hare go up because the lynx were down, and then the lynx start to eat them, and now they're going down. And I drew one arrow there, and here's the other one. And you could just kind of gloss your eyes, and you can get this idea that our populations actually do cycle. It's clunky, it's got edges, it's not a beautiful smooth circle like our mathematical models, but I look at that and I say, yeah, from 87 to 95, we had one complete cycle, right? Predator-prey. That is one complete cycle like this one, right? Okay. Okay. Predator-prey models. They work great with numbers. We like that. They've been demonstrated in controlled labs, like our mites, or even Goss's paramecium. In agriculture and even in medical settings, you can model disease spreading and things like that. It works on short time scales, like the lynx model that you see up there. Actually, it's a pretty long time scale there, but a very simplified system. Not included, just to point to where we're headed further, not included in that lynx and hare, squirrels, alternative prey, mice, chipmunks, nor things like coyote or wolves, alternative predators. Those things get in there and mess up this beautiful system, right? The real world is messy. So, as I say at the bottom here, not so fast. Real populations do not cycle so cleanly. These models are null models. That is, in a perfect setting, this is what you'll see, probably. We don't have any weather or changing climate, changing weather, shorter term, but climates also. We don't have humans getting up there and offering their little stirring of the pot, if you will. So nature is messy. We have to acknowledge that. And I throw in here at the end a dose of reality. As I've just been describing, lots of factors are involved with making those models not so helpful, not as predictive. However, if we go in there and look at a population or a couple of populations and we see that it's not following the predator-prey models from Lotka-Volterra, we can then say, what else is happening? Why is this happening? The null model is just, all things being equal, this is what it should look like. When it doesn't, your job as a scientist is to dig in there and say, oh, okay, I think it's something like, well, predators in this case are inefficient. They don't know how to grab the animals, the prey. They don't know how to find them. They get full. They switch to alternative prey, which is not incorporated in those models, as I've already described. They have multiple predators to compete for the same prey, and those prey can hide, all right? And I don't even include all those ideas like the weather changing things up, or human impacts, or et cetera, et cetera, et cetera. Okay, one more slide before I finish. Well, there's two more slides, but one more concept that's, it's just junked from everything I've been talking about, kind of. But I think it does fit in right here, or at least I'm going to pigeonhole it right here. And that is that if you're looking at predator-prey interactions, so we have the density of prey population on the x-axis and the number of prey being eaten by the predator, there are variations to that theme. And the Lotka-Volterra basically is a type 1 functional response. That is that as the prey density goes up, the predator eats more of them, okay? That actually could go on through infinity in a mathematical model, but we know eventually something happens where you can add more prey, but the predator just can't eat them all. That's a very simplified aspect of this. It's a theoretical model, but it probably doesn't work quite like that. It probably doesn't work that the more prey you produce, the more prey get consumed in almost a one-to-one relationship. Or depending on the situation. It could be a 2-to-1, 3-to-1, but you get the point. It stays constant. Make more prey, get more consumption. More likely, there is what's called the type 2 functional response. So the more prey that are being produced, the more prey that are being eaten, but the curve starts to attenuate, reach an asymptote in a slow way, not this bump, bump, jump, step function, if you will, in the type 1. The type 2, which is the orange line, kind of levels off over time. And what's going on there, it is satiation. That is that the predator begins to have so much food it just isn't hungry anymore. Think of a snake, right, eating mice. Eventually the snake just stops eating mice. Like it eats one and that's it. You could throw more mice in there and it's not going to eat them, right? Because it's full, it's stuffed. It's the Thanksgiving effect. All right, but then there's also the handling time, and I think the snake example is a good one, that in addition to finding the animal, catching it, eating it, finding a way to get it into its belly for a snake, it's got to basically digest it. And it's not going to go out and eat more or catch more until it's digested the last meal, in the case of the snake. So there is a predator handling time of the prey, and that also impacts how many can be eaten, even if you add more mice. A little data point on this, I had connections with the LA Zoo and also a state park, I want to say, in Los Angeles. It was a county park where we had snakes, and we would feed them, mice, and we had owls and all kinds of things. It was a great job back in the day. But we eventually were given a beautiful rosy boa snake, which, if you know your snakes, it's a California native boa, little one, little guy. They're not very big. Beautiful pink. They are in the desert. And the LA Zoo had one, but they threw a bunch of food in there, and that is mice. And the mice basically the snakes stopped eating, but there were still more mice in there, and they started chewing up the tail of this poor little boa. And eventually they figured it out. They got the thing out, saved it, but it had pretty horrendous scar tissue on the tail. So they gave it to the county park site, nature center that I was working in. And so we had it on display. But yeah, it was like, come on, guys, you should know that. Anyway, type 2 functional response, the snakes just stopped eating and stopped running away, and the mice started having their way with the poor critter. Okay, and then the third type, which is called the type 3 functional response, is probably the most realistic. You still have the satiation and the predator handling time causing the curve to reach an asymptote up here. So you can't add more prey and have them eat more because they just can't. But more interesting is what's going on down here. There's a slow growth in the rate of consumption. And that's because early on, prey are hiding in rocks and wherever, and they're getting away from the predator that way. Also, the predators don't recognize them as prey. They have to have learning experience. They have to get in there and see one, try it, eat it, get a bead on it, and now be able to eat it every time they run into it. And increasingly so if it turns out to be a really good prey item. So there's got to be a learning curve, so to speak. And then thirdly, the predators consume more abundant prey early on because they find them more. So squirrels get eaten, despite the fact that hare are around, because the hare are able to hide and the predator doesn't recognize it. Squirrels are everywhere. Chipmunks are everywhere. Eventually, the predator figures out that the hare is a better source of food and switches over, and now you start heading off to the rest of the curve. Okay, so those are the functional responses, type 1, 2, and 3, and for my buck, the type 3 is the most realistic. Yeah? Okay. We're going to head into sort of some fun, 2 fun segments from this lecture. This is segment 2 in the chapter 14, predator, prey, or herbivore chapter. And these are going to be ways, adaptations for the prey to avoid recognition and escape predation. And a lot of this you see in any classic nature program. You see these images, these crazy adaptations that the animals have, or plants. And so we're going to look into some of those, and I just think it's kind of fun to do that. No more mathematical models for the rest of this lecture. We'll come back to those for competition theory. So that brings us to the end of this segment. We'll see you next time. It'll be full of nice, fun stories and pictures about predator, avoiding predator detection by the animals or plants. Okay, so cheers. Have a good afternoon, morning, evening. We'll see you next time.